Come in.
Not as much as I used to.
It looks a lot. Okay.
Okay, welcome back.
We continue.
Part two of Professor Fokas' masterclass.
Yeah. Okay, so let's go to imaging. There's some things here which I forgot, but doesn't matter. Yeah, so I forgot this connection between perhaps where the new method fits, maybe can be thought as synthesis of what of the two most well, at least for linear equations, the two most well-known treatments. One working on the Fourier space, and the other working on the physical space. And maybe this is a synthesis of both of them. But let's talk about imaging. You see, medical imaging is of course extremely important. It is getting more and more credit, not only because of its impact on clinical medicine, but also for its impact in understanding how the brain works. The impact is really enormous. People nowadays consider medical imaging one of the three main reasons why progress will be made with consciousness, you see, but also overall, you see, for example, now, I think every reasonable person considers psychiatry as part of neurology, which was not the case before. And the main reason is because you could not, you do not have any obvious anatomical defects, people suffering schizophrenia or bipolar, etc. But with medical imaging, you can see subtle alterations which you could not pick up before. So indeed, these mental diseases are diseases of the brain, not just behavior. Okay, I remember very, very well when I was in medical school in 83, you see, this is when CAT scan began to be very popular. And with respect to neurology, CAT scan was an enormous advance, because until then, no one could see the anatomy of the brain, you see, of the living brain. So neurologists were very good to isolate the problem. So from the defect you had, you could go back, but of course, they knew that most likely this was a part of the brain where the problem was, but was it an abscess, was it a tumor? They didn't know, you see, they could not see. So CAT scan and then MRI had an enormous effect on neurology, but then of course, they had a huge impact in many other diseases. So now you cannot think of medicine without CAT scan and MRI. People are surprised when they learn that these techniques are based on the solution of mathematical inverse problems. They're really very surprised, but of course this is the case. Cormack, when he got the Nobel Prize in 1979 for CAT scan, and if you read, it's very interesting, if you read his Nobel Prize acceptance talk, he says that it was clear to me from the beginning that the problem of tomography is a mathematical problem. Very clear statement. Of course, you see, as you know, CAT scan is based on the inverse Radon transform. Yes? But Cormack didn't know about the inverse Radon transform. I mean, Radon had solved from 1917. I remember this because of the Russian Revolution, you see, but not many people knew about the solution. And of course, what is the Radon transform? The Radon transform is the simplest transform you could never imagine. You have a function and you integrate along array. I mean, what more generic, you see? And this is the reason why many people have resolved this problem, including Gelfand, by the way. One of the reasons, open parenthesis, that Gelfand, developed this integral geometry, etc., because he was very, very upset that he didn't push the CAT scan business when he was told to do so. But anyway, still, when I was in medical school, the idea that you will have medical techniques that not only will be able to, through which you will not only be able to see the anatomy of the brain, but you will be able to see the brain at work. So the functional problems of the brain, as opposed to the anatomical, nobody considered this seriously, you see. But now, of course, this is a reality, not now, but many years ago. And there are various techniques, the most important of which is PET, positron emission tomography, SPECT, single photon emission computerized tomography, and functional MRI. So what are the mathematical inverse problems associated with them? Functional MRI, like MRI, for most cases, is inverse Fourier transform, so it's not, from our point of view, very interesting. And PET, there is a serendipity. The serendipity is that the two gamma rays that are picked up by the PET machine go in exactly opposite directions. And because of this, there is a very nice cancellation. And because of this cancellation, instead of having the so-called attenuated radon transform in PET, you have the usual radon transform. So the mathematical problem of PET is identical with the mathematical problem of CT. Huge serendipity. But not the case with SPECT. And just a couple of words, you see, I have completed a book, a chapter, there are 6, which talks about medical imaging techniques, and I always try to use, to illustrate each of those techniques by an interesting medical case. So for PET, for example, I discuss Alzheimer's, you see, because this is this big debate, what is the most important reason for Alzheimer's, are the plaques or tau protein, etc. And now there are different studies you can use. You can follow using PET of one or the other, which is extremely important. Has really revolutionized how you can follow Alzheimer's patients. But even more dramatic is some work which was done here by Owen with respect to functional MRI. And I don't know if you're aware of this, but very quickly he was able to communicate using functional MRI. He was able to communicate with patients that they were supposed to be in vegetative state. Vegetative state means that basically you're a vegetable, you see, and these people were completely unresponsive, etc., and remarkably turns out that 1 in 5, I mean, it's unbelievable. It doesn't just happen. 1 in 5 of these patients were communicative through functional MRI. So what did he do? It's a long story, but very quickly, it turns out that a lot of functional characteristics are very robust. So you see, for example, if you tell somebody, if you tell Mark, close your eyes, Mark, and imagine you're playing tennis, you see, then there will be a particular part of your brain which will be activated. You see? And this, you can pick it up with functional MRI, and this will be the same with anybody else. You see? And similarly, if I ask you, imagine you are navigating in your house. Again, there will be another part of the brain which will be activated. So, this was known, of course. So they did this to these patients, you see, and they saw activation in these areas, you see, which was shocking. Once then you do that, then you can go much further. This work was published in Science. You can go much further. So they would ask them, if you have a brother, imagine you are playing tennis. If you do not have a brother, imagine you're navigating your house. And this the answer this way, indeed, they confirmed that their mother, they were dead, etc. So this is fantastic. So just give you an idea of the great. But there are many more things. You see, for example, when you do a hard calculation, we know which part of the brain is working more, etc., etc. So, but I could talk more than 1 hour about these fantastic developments. So, but let's go to mathematics. So the mathematics of it is, again, solving some particular inverse problems. And as I already mentioned, with Gelfand, we understood that, you remember, this morning I wrote that the x part of the Lax pair of this linear Schrödinger was mu x plus minus ik mu equals u. You see, if you generalize this just slightly, so you put a second derivative there, so I have not only one variable, but I have two variables, then it turns out that the analysis of this equation, and I will explain, that's the only concrete thing I will do, that the spectral analysis of this equation, and I will tell you in the next transparency exactly what I mean by that, gives rise to two-dimensional Fourier transform. And as I said this morning, an honest two-dimensional Fourier transform, not just iteration of two one-dimensional. So we understood that with Gelfand, and as I said, this paper, although was published in '94, was really done in '91, and at the time at Clarkson, the young Roman Novikov was visiting me. I was excited with this paper with Gelfand, so I said, I knew that Roman was interested in Young-Mills equation, and the linear limit of Young-Mills is radon, really. So I asked, I said to Roman, let's do this problem. So we analyze this equation, and out of this, we got the radon transform. Okay? But this is working too hard, because, you know, as you probably know, you can do this much easier by using a two-dimensional Fourier transform directly. That's how radon did it. But I just want to, and of course, our paper could not have been published with this only, so we added some discrete version of this, and the paper was published. But then I was at Imperial one day, and I learned about this paper of Roman 10 years later. And this paper analyzed this equation. As you see, this equation is a very small variation of this. Yes? You only add this term, Mark. Look, you only add this term.
Non-constant coefficients.
Huh?
Non-constant coefficients.
Yeah, but only this variation. You see, but it's first order. So I will tell you. So you add this, and then what happened is out of this analysis comes the big result. The big result is that because of this, Roman was able to obtain the inverse attenuated radon transform, which plays the same role for spect that radon transform plays for PET. This was a huge result, because you see, Brian Hutton is one of the best persons in PET, and he was telling me he would give talks telling them why attenuated radon transform will never be inverted. You see, because they have some X invariance, X translation, etc. So when I got this result, I was both happy and unhappy. I was both happy because it was the first time that our method with Gelfand was used for something non-trivial, but I'm happy I didn't do it, you see. So I started working on this problem, and immediately I understood that, you see, if this was an OD, you would absorb this by integrating factor, you see. And essentially you can do the same. So this result can be obtained from our early result with Roman in a couple of lines. But more important, I began, this is around the time when this institute of mine, this institute in the Academy of Mines was created. So I told these people there to concentrate on this. And everybody thought that I was crazy. You see, because in PET, you have two ways to do PET. One is something which is called filter back projection, which you probably know, and filter back projection is nothing but the numerical implementation of the inverse radon transform. But the inverse radon transform, as you will see in a moment, has in it the Hilbert transform of the radon data, right? And because of the convolution, people use Fourier. And this is the filter back projection is numerical implementation of radon in the Fourier space. You see? And there's an alternative way, which is called OSEM, which is iterative, which does not use any exact formula. And this is what they use now for what happens for spect. For spect, you could say that they only could use OSEM because they didn't have any analytical formula. However, because OSEM is slow, and because they do many specs, they were using feedback projection, which is the wrong thing, by assuming, I'll show you in a moment, that the X attenuation coefficient is constant. So, but when I told them, they said, why you want to do this? OSEM is so successful, etc. Anyway, I convinced people to do this, and after 10 years, we produced these two papers, you see, which show that in some sense I was right. But before I tell you a little bit about the practical implications, let me please tell you for the first time some mathematics. Okay, so what does it mean? I even use this terminology in the morning. What does it mean to do the spectral analysis of this equation? Okay? I say I'm going to do the spectral analysis of this equation. So what do you do? The first step you do is something which more or less it's obvious, because as a mathematician, instinctively, if you look at this equation, the first thing that your brain does is drives you to think that f is given, and you solve this equation for mu. Okay, that's all. So I'm asking you to do this, but with one caveat. The caveat is you should be able to do this for all complex values of k. This is the crucial statement. Usually when we solve these equations, we solve them for real eigenvalues, see? But you should solve this for all complex values of k. Okay? And of course, we know in mathematics that it's very important to use the correct coordinates. Yes. So because we have two variables, I introduce this new variable. Now, so I go from x1 and x2 to zeta, but also zeta bar. Yes. If I take zeta bar, I will have to take bar of this, because remember, k is complex. So I have two equations. All right. I make change of variables. So I go from x1 and x2 to z and z bar. And the reason why I chose z in this form is that in this new formulation, this equation becomes very simple. Namely, this equation becomes marked a d-bar problem. You see, in physical space. In physical space. Not in complex space, in physical space. Okay? So now, if I impose some additional boundary condition to this, I can have a unique solution. Yes? So, Pompidou is the one who inverted this operator, by the way, trying to solve a problem that Painlevé posed. And if you do this with this boundary condition, the answer is very elegant, and it's this. You see, this is the answer. So we're done in the first step, namely, if you give me f, I can give you mu. But what mu, Professor Rich? For all complex values of k. Yes? Now look, there is a jump, because when absolute value of k is 1, there is a jump. I mean, it's not well defined, you see? And actually, if you look at this function, you see what? You see that the only k dependence is here, which of course, if I go inside and outside the unit circle, will disappear, and the only k dependence is in here, right? Because remember, z from the previous, z is defined here. So here is the dependence on k. Okay? So I have an expression which is well defined for all complex values of k, and I see it has three representations, one inside the unit circle, but now that's the complex k plane, and one outside. Okay? So now I ask a question that if you are not used to this business, it's a very strange question. But we ask it, and the second strange question is the following. The strange question is, I have a solution which has some fantastic property. What is the property? The property is, it is well defined for all values of this complex parametric k. Can I use this fact to obtain a different representation for mu? Okay? And the answer is yes. Because if, for example, you knew it was analytic for all values of k including infinity, it will be 0, right? Well, if it was analytic everywhere, you would have uv. But now, since you know that it's analytic inside the unit circle and outside the unit circle, all you have to do is compute the jumps across. Because if you have the jump across the unit circle, then this will give rise to a Riemann-Hilbert problem that Alexander talked a couple of weeks ago. Okay? So now the question is the following. I have a representation, and what I'm going to do is I'm going to do a delicate analysis to find the limit of this when this k, which appears here, approaches the circle from inside and inside. That's a calculation, you do it, and if you find this calculation, you find that these are the limits. You see, the limits of this function when k approaches the unit circle from inside and outside are given by this. Now what you have here? You have some function here which is relevant. Why is it relevant? Because I'm going to take mu plus minus minus, therefore it will drop out, you see? And then I have here some projectors, people know what they are. And what is this? This is the Radon transform. Okay? Therefore, now you have the jump mu plus minus mu minus defined in terms of the Radon transform. But then you solve this elementary Riemann-Hilbert problem, yes, and you find a new representation. There it is. So, in summary, by doing something naively and solving nu for all f, in terms of f, but for complex values of k, you are able to find this representation. By exploring the fact that you have a function which is sectionally holomorphic, and by finding the departure from holomorphicity across this boundary, you are able to define a Riemann-Hilbert problem, and so that you are able to formulate, to find another representation. But they are the same, which means you have a relation between f and hat, and this is the inverse Radon transform. Okay? And this is what we use for all these problems, all right? So this is interesting because it's quite a rich problem, because the direct problem is a Debar problem, and the inverse is a Riemann-Hilbert problem. Okay? In spite of the fact that it's a two-dimensional problem. Okay, so this is how we solve the problem with Roman-Novikov. So this is a derivation of the Radon, and a very small variation of this gives. Now, how can we use this? How can we use this? You see, I was not interested in PET because we didn't have anything new in PET. You see, the formula was the same. However, I decided, under the push of my colleague here at Cambridge, Shirley's, because we knew we could not use Fourier transform methods for SPECT, want to use some other things for PET. So to get some experience, we went to the PET that everybody has done, but instead of using a numerical implementation in the Fourier space, which is what would be consistent with my method, by the way, we did a Fourier representation in the physical space. So just a couple of lines, what we did. By the way, a quick statement is why should one use exact methods, analytical methods, as opposed to set? And there are certain advantages that you see here. And now, this advantage become more and more prominent because what? Because now there is a big push in the United States to minimize the amount of radiation. And it turns out that for radiation, analytical methods lower radiation, analytical methods done better, and ours does even better, as you will see in a moment, so-called cold regions. Okay, so this already we discussed. So this is a mathematical definition of Radon transform. So I'm going to integrate along a line. Yes, I'm going to integrate along a line. I parameterize this line by going the pseudo distance and some parameter along. Therefore, I introduce these new coordinates, which are my reparameterization of this line. Yes, so I take this line, I write it in terms of the new coordinates, yes, and I integrate along tau, and I find the function of rho and theta, and this is the Radon transform. Question: if I know this for all rho and theta, can I reconstruct the function? That's the inverse problem, yes? And we already derived the inverse formula, and this is what happens. So what you need to do, you need to take, come on, there you go. I know what I will do, You see, so what you need to do is, you take your data, you compute each Hilbert transform, as you see, and then you put it here, you take this integral over theta, and then you take this derivative, but you can simplify, and if you simplify this is the final formula. Remember, F, capital F, is the Hilbert transform of your data, yes? So you compute this, you replace rho in terms of x1, x2, and theta. After you integrate over theta, you end up with a function of x1 and x2, which is what you want to reconstruct. Okay? So all we want to do is to implement the simple function numerically from knowledge of the data at certain points. Okay, so I want to give you this, I want to draw the main idea. The main idea is rather, you see, and this is the reason why people use field projection, because the Hilbert transform is a convolution, therefore when you do Fourier, it simplifies. But instead of doing this, because we want actually to get some practice, we do just cubic splines. You see? And these coefficients can be written in terms of the value of the function at these points, which we know, these are our data, and also second derivatives, which you can compute by imposing continuity, you see, of the first derivative, etc. The details are not important, so we found certain formula, which then we want to check. And you see, this took us about 10 years, you know. And the reason it took us about 10 years because, you see, it's very hard to do real problems, Alexander Ritz. It's very hard to do real problems, you see, and to compare with the standard of the industry. Because, you see, to do real problems, you have to have real machines, you see. And then how do you compare? To compare, you see, you have 3 levels of comparisons. The last level is clinical, right? Who will see a tumor better? But this is not very well defined question because you don't know where the tumor is. So you cannot compare at this level. But the first level is you do computer simulations, and for this they have this very nice phantom that you use. But my best, the one I love very much, is the second level. What is the second level is you use real phantoms. So you use the phantom, so all these are simulated, all these are, but you use this. You use this kind of phantom, which is a real thing. So we have it in my center. So you put in there the medication, you see, you put it in a machine, and then you get real data. You see, and this is real data, but you know the real object. You see, so now your comparisons are beyond any doubt. Now you know exactly who does better and who does worse. You see. So I like this very, very much, these real phantoms, you see. So using all this, we have been able to make comparisons, and I give you the answer before I go quickly to. So we did all these comparisons. Okay, but comparison of what? You see, there are certain parameters which the industry uses, like the contrast. It's the contrast of hot regions when there is medication, and the cold regions where there is no medication, and the bias are 2 most important parameters, you see, etc. So, and these are real data but never mind, because as I said, for this, you cannot really get too much information. So this is the answer. So the answer of these 2 papers that we saw before is that, surprisingly, this technique does very well, you see, and after discussing with Iserlis a lot, I was expecting that maybe we would do slightly better than Peter projection, but it turns out that we're very competitive with OSEM. You see, when I say OSEM and 2, because OSEM in clinical practice uses 2 iterations. Of course, if they were doing something experimental, they can do up to 10 iterations, and some of these results, they are as good as ours at 8 or 9 iterations. But again, the question is you wouldn't know where to stop, etc., etc. So we're very happy with this. But remember, this was for me a practice problem. The main problem is to do SPECT, which was this. You see? So this is the attenuated radon transform. So let me explain what it is. You see, you take an integral of the function g. G is the function you want to reconstruct. You see? This is the data from your SPECT machine, and this f is the attenuation, which is you have to do a CAT scan to find f. F is what we do. So if I give you f, and if I give you this, can you find g? And this is the formula that Riemann first did, and then I rediscovered. You see, as you see, this is more or less what we had before, but this function now is much, much more complicated. You see, you have projections of projections, etc. But doesn't matter. I mean, you can still numerically implement this formula. You see. So what people do is, if you assume that this f is a constant, then it goes outside, and this becomes the usual Radon transform. And this is, for example, if you go to because Hatton is at the University College London. If you go to University College London and have a spect, they will use Fidelbrat projection at this level. Because if they do a SEM, it's much slower. And they do continuously. Okay, so our goal was to implement this formula using this cubic spline, which we call attenuated spline reconstruction technique. By the way, this technique is the only technique right now which is in the commercial library among analytic techniques. And again, you do all these tests. It's a very long procedure, and you compare again bias and contrast, and these are various results. But it's not important for us. You see, this is I like it very much because this is real data of this Lorenzo phantom. So you put holes, you put medicine in these holes, and you try to reconstruct it. Even by the eye, you see that this is much cleaner. So this is Fidelbrat projection, and this is our technique. And this is the quantitative. And this is our final paper in 2018. So I started this business in some sense with Gelfand in 1992, you see, and this is where finally this paper was published. So again, this paper claims that, of course, as you expected, this is better than Fidelbrat projection because Fidelbrat projection was an approximation, but it's even at least as good as OSEM. So I finished the second part of my talk, and now I talk about the asymptotics of Riemann. Unless there are any questions here, because this part will not come back to it. Yeah. Questions, or we move on? We move on. So what is the problem with Lindelof? Okay, so this is the paper that assumptions have just appeared, where I will tell you what are the main results of this paper. This is, in some sense, a paper that I've been involved, I'm trying to write for the last 10 years, maybe a little bit longer. So what is the problem? The problem is, you see, you all know the Riemann function. The Riemann function is defined actually by Euler in a very simple sum. Of course, the only problem with this sum is that in order for this sum to make sense, the sigma must be greater than 1. You see? However, Riemann, who was the god of the complex plane, understood that he could give an analytic continuation to this problem and define it for all complex values of S. Yes? And indeed, he did this, and he wrote an integral representation, which I'm not writing, an integral representation for the Riemann function, and you have an integral representation which makes sense for all S. By the way, S could be Z. In this case, it would be X and Y, but in honor of Riemann, people are still using S, with real part sigma and imaginary part T. Okay? So you have now this integral representation, yes? And you can start, therefore, looking at the properties of the Riemann function in the entire complex plane. In particular, you can try to see if this function is ever zero. And Riemann speculated that there are some trivial zeros you can see immediately along here, but among the non-trivial zeros, Riemann speculated that the only other places the zeros will be on this ray and nowhere else. You see, Hardy and Littlewood from Cambridge, they proved that indeed on this line there are infinitely many zeros, but no one has proven that there are nowhere else zeros. Yes. And it turns out, because of symmetry, etc., it is enough to look in this open domain here to make sure that there are not zeros there. And then Riemann hypothesis will be complete. Actually, of course, you can start doing this numerically, and people, at least up to a year ago when I made this transparency, up to 10 to the power 13, they could verify that there are no zeros. And of course, 10 to the power 13 is a very large number, but it's very, very small with respect to infinity. But already tells you that the main problem with a Riemann function, with a Riemann hypothesis, is what happens for large t. For small t, you can more or less do everything by hand. See? Of course, people realize this, so Lindelof tried to control the large t asymptotics of this function. See? What happens to the Riemann function for large t? And he speculated that it has a certain behavior. And this behavior is valid for the entire forbidden domain, but to make things simple, I'm only telling you what happens on this critical line, and it takes this very, very simple form. Okay? So it tells you that it grows less than any algebraic power, but of course it could go like log t, etc. And then once you go to log, it's very difficult to things even to check numerically. See? Okay, so this was the speculation of Lindelof, and then people understood that this was a very important question, deeply related to Riemann. In what sense? It turns out that Riemann implies Lindelof, but Lindelof doesn't imply Riemann, however, eliminates a very large number from Riemann. But also, in my opinion, gives you very, very strong information. You see, maybe even more than what Riemann hypothesis says. So, if you look at the history, which after I wrote this paper, I started looking carefully, more people, more important people, more famous people worked on Lindelof hypothesis and on Riemann hypothesis. And then Hardy had with Lindelof this great result, and the great result is that he was able to prove this, but instead of having epsilon here, have 1/6. You see? And for these results, they stayed there for something like 85 years. At some point, people even thought that this was the best, that this was all, but then Huxley brought the ATP down, and people made very, very hard work in order, and I will tell you why, in order to bring it further down, and the final best result before his death was Bourdieu, but he could not reach 1/7. Okay? Okay, and then there are people like John Harner, never mind, there are people, there are famous people, who claim that this result will never be proven, that Lindelof hypothesis will never be proven by itself, and the only chance you have to prove Lindelof hypothesis is to prove Riemann, because Riemann implies Lindelof. What is the reason why people make this statement? The reason is very natural. You see, the reason is very natural in my opinion. All the attempts, all attempts up to now to prove Lindelof hypothesis are, in a sense, conceptually elementary. Okay? What does it mean conceptually elementary? It means the following thing. I told you already that you have an integral representation for the Riemann zeta function. You go to the integral representation and you do asymptotics. You see? You do asymptotics, right? And you compute the first term, and the first term turns out to be this. You see? Which is, of course, the sum you started with. The only difference is now the upper limit is t instead of infinity. Therefore, this now converges for all values of s. Right? So you're done. What is the problem? The problem is that this Mr. Darren is a transcendental sum. You see? Therefore, now the problem reduces to finding techniques to estimate these sums. But let me repeat, you find techniques to estimate. But everybody knows that in estimates, you always lose. You see? And this is the reason why people claim that you will never be able to prove Lindelof hypothesis directly. Okay? It's a very legitimate, objection. Okay, from the beginning, under the influence of Gelfand, etc., my approach was not, of course, to try to estimate. I'm not good at all at estimates. Not try to estimate the sum, but to embed the Riemann function maybe in a bigger problem, in a different problem, and do it indirectly. Of course, this is maybe a good idea, but how do you find this problem that you embed? You see, there's no guidelines. It's not like here that tells you do asymptotics. There go, anything goes. So, of course, one of the reasons why I've been working with Prof for many years is because I had various attempts fail, and then you have to start from scratch. But in this process, in order to get some confidence and also, it turns out, some useful information, I decided first to go back to the usual asymptotics and do something heroic, and I wouldn't have been able to do this without Jonathan Reynolds. And this is to do asymptotics of the Riemann zeta function to all orders. Okay? This sounds impossible because anybody that has done asymptotics knows that the higher you go to asymptotics, the worse the situation becomes. But this is not the case with Riemann. The Riemann function has the property that the higher you, everything after the next term is explicit. It's only the first term that is transcendental. So in principle you can do it. And Riemann made some notes which Siegel read and wrote a paper when he did this for some particular case. You see? And with Jonathan, we extended this to all cases, and that's why it was accepted that the memoir of MS, it's in the list of papers to be published. I hope it will be published very soon because this work was done several years ago now. And I just gave you the first couple of terms to give you an idea of the complexity of this. Okay? But this, it turns out, it is not only, of course, you cannot say anything about the Riemann hypothesis because since the first term is still transcendental, but it turns out that it's very, very useful for what I will tell you in the future, next. But again, this is just a parenthetical remark, but very, very useful. But the question is, back to the Lindelof hypothesis, back to asymptotics. How can we do, what can we do with that? So I was searching for places to embed Riemann, and finally I found something, which is this red identity. First of all, I'll tell you what it is, and then how I found it. So you have the principal value integral, because at r equals 1 you have a singularity. You have a bunch of gamma functions. You have the square of the absolute value, which is perfect, because this is what you would like to control, you see, equals something which is given. This function, as you see, is absolutely explicit. In particular, for the 1/2 case, is the how do you call it, function, Alexander? Gamma prime over gamma. That is. Huh?
So this is the logarithm derivative of gamma function.
Okay, so absolutely explicit. You see. So you see, in principle, if you go here, in principle, if I was strong enough to solve this equation, I will have the absolute value equal something explicit. You see, I cannot solve this. We attempted with, we thought we had actually with Jonathan, we couldn't. So what I'm going to do is I'm going to do large T asymptotics of this equation and hope for the best. See? The difficulty, the problem with this is it is not clear that if I do large T asymptotics here, I will get the large T asymptotics of the Riemann function. I might get something else. Okay? How did I find this equation? These equations, I told you, is the result of a many-year search, and then with a very, I would say, a brilliant former student of mine, Anthony Asson, maybe the most original among all my students. We were trying to connect the Riemann function. You see, there are two generalizations of Riemann function. One is called Horowitz function, and when we did this, we found some relationship between Riemann and Horowitz. And then manipulating this relationship, I came up with this equation. Okay. So the rest of my 15 minutes, hopefully less, I will tell you what happens if you do large T asymptotics of this function. Okay. First of all, you know that this, for most values, decays exponentially. You see, therefore, very quickly, you go from minus infinity to infinity to a finite interval using the exponential decay of the gamma functions. So you introduce these parameters, delta 1, delta 4, between 0 and 1, and then you go to a finite interval, and the error you make is exponentially small. No problem. Okay? So this is trivial statement. But what is important now is the next statement, which is you want to split this interval appropriately so that you will be able to do effective asymptotics in here. And it turns out that the correct way to do it is to split it, or a way to do it is to split it in 4 intervals, which are these. You see, you begin introducing these parameters, which, by the way, when these parameters were introduced, I was very happy with them because, as you saw with Lindelof, there was this epsilon. But the epsilon comes from where? Riemann doesn't have an epsilon. So then my hope was, and it's indeed the case, that this epsilon will come from these deltas. You see? So you go to this. So now I have to do asymptotics in each of these intervals. So let me tell you quickly what happens in each of them. The first interval for these values of delta 1 sufficiently small can be done explicitly. It's not a problem. And this is rigorous result. And the second is rigorous, but the second result already uses the most powerful result of the asymptotics of Riemann function, namely Addison estimate. Addison estimate is used in order to obtain this result. So I1, I2, no problem for these values of delta. So now we're left with 2 integrals, I3 and I4. Remember, here I never used any information, any asymptotics of Riemann, but to go further, there are 2 ways to do it. Remember, I4, these integrals, having it a Riemann function, you see? So there are 2 ways. One way is to replace this identity that I started with an identity which involves sums as opposed to this, or to keep track the errors. And now we have done both. To keep up the errors, if I replace this by the leading asymptotics. And this is why it was very important to have a very good estimate for the second term. So I will only concentrate on the leading term, which means what happens if I replace this by the leading sum of the asymptotics. And I do this, and if we go, so hat is to remind you that I have replaced inside the Riemann function by the leading asymptotics of the Riemann function. And then I take this sum, where, as you see, is because I replace the Riemann by the leading sum, and if I do asymptotics, it turns out that asymptotics is not hard in a sense. Namely, we always know that we get main contribution for trivial integrals from stationary points and from the boundaries. From the stationary point, we get this sum. See, and from the boundaries, we get this term, which I didn't write because there's our cat. So what is the only difficulty? The only difficulty is that it turns out that one of the stationary points could coincide with the endpoint of integration. And although this was formally done by various people, some of which we know, we could not find any rigorous treatment of this actually. And this is this paper. This paper is uniform asymptotics at the stationary point approaching the endpoint. So this was under control. And then we had to do I4. And here we needed some novel asymptotics. You see? So you see there are these 2 terms. So this is the stationary point again, which is trivial. But there are 2 novel terms. And one is explicit. But this one is defined through this complicated integral. I cannot go to the details, but this is what it is. Okay? So finally, you want to put all this together. But before you put them together, you see the following. This is the Riemann sum. Yes? This is the square of the Riemann sum. Right? So this is the leading term of the I4. But the leading term of I3 is this sum. And it turns out that there is a relationship between them. So this is the next part. So here, you see, this sum is what appears in I4, and this sum is what appears in I3. And these 2 identities relate these 2 sums in terms of some small sums which we control by using the extension of the classical Hardy work, etc., for double sums, which was done not by us, but okay. So these are the relations between these two sums, and plus some estimates, and these estimates were published here. You see, the advantage of this method is that we have to use estimates like Hardy, like 1/6, etc. But fortunately for us, these estimates are in the error terms. So they are not the leading terms in asymptotics, so they don't bother us too much. So finally, you put everything together, and if we concentrate on the case 1/2 for simplicity, this is the answer. So this is the result of the large T asymptotics of this identity. See? What is good and what is bad about this result? What is good is that this, as you see, is the square of the Riemann function. Right? The right-hand side is Lindelof, where this epsilon actually is a combination of the deltas, etc. But unfortunately, these sums are not the full sums. So this is not the full Riemann function. It's not the square of the full Riemann function. So what the statement is that using this identity, we can say that a variant of the Riemann function satisfies Lindelof's hypothesis. But of course, people say, I don't care about variants, I want to know about Lindelof's hypothesis. Still, it's the first time to our knowledge that a variant of Riemann function has been shown to satisfy Lindelof's hypothesis. Okay? And my paper is not completely rigorous because of the error terms, but basically this is now almost complete. Okay? So this is our first result. Our first result is that a variant of the Riemann function, in the sense that the integrand, if you want, is the same, but the boundaries are not full, satisfies Lindelof's hypothesis. What about Riemann function itself? You see, in this business, as we saw, I introduce various deltas by chopping. So I have a lot of freedom. Okay? This was the result of, if you want, the most, without using any properties of deltas. So if you do slightly more, and this paper already has appeared, if you do slightly more, it turns out that you can, by the way, you remember these things appear in I4, as you remember, all right? These will have these estimates, which, as you see, they remind you of Hardy's estimate, which is indeed the case because it's the same proof as Hardy, but for double sums. For double sums. You see, when I started doing this business, I knew that doesn't matter what I'm doing, at some point I would have to use these classical estimates. But I don't like reading other people's papers, you see. So I was trying to persuade my students to someone to do this. And finally, Kalimeris became an expert, not only on single sums, but on double sums. And that's why his contribution is vital. So this, using this, we're finally, for some value of delta, which I state, we're able to get this equation. So this is the final result. So if you look at this equation, look, the right-hand side is t to the 1/6. Okay? You have Riemann square, and you can very easily show that if you do iteration and you replace this by this, you find the same thing. Okay? So it means that at least formally, it tells you that Riemann square is 1/6, which means Riemann is 1/12. Okay? So what we're doing now is going to these results with Jonathan. We're halfway through, and every single line is rigorous. See? After this is done, then we will claim that we have the 1/12 result, which of course, which is a quantum jump. The reason why people got so excited, by the way, with the last result of Bourgain is because there are now some estimates that if you follow the classical approach, you will never reach 1/7, and what Bourgain did was very, very close to that. So this will, I hope, convince everybody that this is a completely new way to this problem. But as I said this morning, always you have to ask why you get something better, and the answer is There are three answers. One is in terms of estimates. We use everything they use, but even for double sums as opposed to single sums. But on top of it, we use this novel asymptotic, which I didn't explain, for I4, and we use this miraculous identity. Both Jonathan and Lennox and Kalimeris claim that they can do better than the 112 because then they can start bootstrapping, but I'm not interested. I think this is this would be absolutely good enough. Thank you very much.
Thank you. Any questions?
I'll ask a question. You have two integral equations.
Again?
You have two integral equations. One here
Yeah,
for large T, and then one
For all
the
T.
first order
for all
integral equation.
the sub one, the original one.
The original one.
Yeah.
Now, that one
Yeah.
is first order integral equations, so
Yeah.
iteration isn't enough. How do you solve that rigorously?
Solve? No, no. If we could solve the first equation, we were done.
I know.
No, no. We
How do you know
cannot.
there's a
Unfortunately,
solution?
no.
But it's single integral equation, so it's not regular kernel then.
But it's a
So
first
what's wrong
order.
with the theory? You can write
I'm asking,
negative theory.
you know, maybe you have the answer, I don't know.
No, no. You see, we have a rigorous derivation of this equation, starting from.
Right.
So there is no doubt about this that this equation is correct.
But solving for K or zeta squared in terms of G.
I don't know if I don't know anything. All I know is that this is an identity. So starting with the gamma and zeta and following absolutely rigorous step, you come up with this equation. So this equation is correct.
Understood.
Yeah.
But at
So
some
from-
point, you want to invert that equation.
I'm sorry?
You want to invert that equation.
No, I would like to, but I cannot. So what I want to do is I go to this equation and I have an identity, and from an identity I obtain new identities by doing large T asymptotics. You see? So large T asymptotics, you see, originally when I was talking to a top expert in this business, says this equation cannot be true. I said, why cannot be true? He says, because we don't know it. We have been known by now. So after I convinced him the derivation is true, he says, okay, it's true, but it's useless. Why it's useless? You see, because you want to get information about this, but this is not like a delta function. However, then I convinced him. Then I told him, no, I'm not. Don't get point information. I won't get asymptotics out of this. So this is what I'm doing. So every step. So you derive this equation, and from this equation, since the derivation is rigorous, you have the right, step by step, to obtain any information you want out of this. And the first information we got out of this was this result, which tells you that this function, call it mark function, this function satisfies the Lindelow's hypothesis. Okay? This function, as you see, its kernel is Riemann, but not the sum unfortunately. So that's the first result. But there are many other results you can get for this. So a next result we got out of this, but this is formal, is that out of this equation now is valid for the Riemann function.
This is a second order equation. Well, because you have the extra order.
Yeah.
So you might argue, okay, you can do it by iteration.
Yeah.
and so
But
on and so
again, of
forth.
course, this is how
That's
we'll
what you
establish
want
in
to
English.
do.
But
I'm
again,
only pointing out
again,
that
there's a
first order
difference.
equations.
Mark, but there's a very big difference between our treatment of this and this. This, indeed, we want to solve this equation for this in terms of the right-hand side. You see? The top equation, we don't want to solve it for. We want to get right. We want to get properties out of it.
I understand. I'm only saying that they're often ill-posed, they're difficult, and sometimes they're kernels.
You see,
They're
by
not
the way,
very-
But it is non-linear, Mark. It is non-linear.
It's a first order, I mean, it's a first order,
Does that
but
make it easier?
It is non-linear.
if you
No,
put
it's-
tau
This is
t
why
as a
you
new
have
variable and
But-
tau
double
equals.
sum.
But it's non-linear, just
Non-linear.
call
Huh?
zeta squared x.
What
They
no.
sound
No, it's
fast.
linear, you can
It's
just
linear.
call it
This
as a
is
new
respect to
function.
zeta function.
Yeah, it's linear,
What? With respect to zeta function,
Mark,
it
but
is
that doesn't mean
non-linear.
it's easy.
No, with
No,
respect
Mark,
to zeta function,
Mark,
it is
you see,
non-linear.
your point would have been a good point. If
It's
and only
non-linear
if
equation.
I was trying to solve this equation for this function. I'm not
Yes.
doing this.
But you can do asymptotics
Yeah.
on this equation.
I'm going to get from one identity as many other identities as I can.
Well, this is why he got the double sum, not
Absolutely,
the
absolutely.
first sum. Well,
It's
this
always
is
double
many
sum.
equations, so
It's always double sum. And this is why, by the way, the reason why people got interested in double sums is because they were expecting that from double sums we get better estimates than from the single sums. And indeed, that's what we see here. You see, remember, this 1/6 at the last equation, it is Hardy. You see? This 1/6 is Hardy, comes from Hardy, you see? But the square of this is 1/6, so this is the whole point. Okay.
That part I understood.
Okay.
Any other questions? Now, you said earlier this morning that you were unhappy with your starting point.
Yeah.
Is this the?
Of course.
You don't know how to.
No. I mean, you see, the starting point is this equation. How do you motivate? How do you motivate this thing?
Yeah.
How do you motivate this thing? I mean,
But if any progress with this equation, what would be done
Sorry?
after that? If you have certain progress with our one equation, so what would you do next? Do you make?
You mean if he
could you
doesn't-
make a better conclusion about this? I mean, that is something that you interested in. So it assumes that you're
No, I'm not
successful with
interested
this
in
equation.
I'm not interested in this equation at all.
Oh,
What
you're
I'm
not
interested is at consequences of this equation. I'm not interested in this equation. For me, this is a tool to get information about this. And already, this equation gave me two pieces of information. One
But you
was
said
not
that
directly on
you
this.
wanted to solve it and couldn't solve it.
Right. Maybe I shouldn't have made this statement. My statement was just to motivate why it seems that this has information. Because if I could solve this equation for this function, then I would be done. Because this is given and this is given, so I would have some explicit elements. However, obviously, for what Mark already said, this equation cannot be solved. But I don't care. So for me, this equation is a tool. From the beginning, I said that my goal was to embed the Riemann function is something bigger, some identity, so I could get indirect information as opposed to doing direct estimates, you see? And I had many trials, and finally, by the way, this equation is very, very, very sensitive, because when, for example, I got this sum, the first result was this. When I got this sum, then I said, can I go back, now that I know what I'm missing, and modify this equation, so that I get, instead of this, I couldn't do it.
Frequent equation of the first type, so without.
And the question is, so I don't know how, when I discussed with Atiyah this problem, which as I said, is when Atiyah came back to Riemann, he said, I don't know how to motivate this. Atiyah said he would, but he never did, you see. I still don't know. For me, it was this result, if I should have written this equation is much, much more complicated than this, but somehow this motivated to do this. Of course, this equation can be derived from first principles, so there's no doubt about its validity. And by the way, the last statement was very, very important. At some point, there was a computational error in the I4 integral, actually. And at the beginning, we thought we had exactly Riemann. And I just want to say that every step of this asymptotics has been checked numerically, you see? So this is a great advantage. And this step was not checked. And it was Jonathan's fault. And finally he checked it, and he says it doesn't work. And then I went back and I found error in the asymptotics. But the advantage we have, of course, instead of the classics, is this, because you have an exact formula, you do asymptotics, and you compare. And so everything is absolutely correct. And as I said, I think you can go more than the 1/12, but it's such a quantum jump with respect to what is done that there is no reason to go further for me. After all my problems are 10, 15 years, and I'm running out of time. I'm running out of time.
Another 25 years, no problem.
Maybe, okay. That's it.
Do we have any more questions for Thanasis? Well, let's end by thanking you very much for
My pleasure.
Now I'm going to